All right. Well, hello, everyone. Good morning to those here in the United States, and good afternoon to you all over at CERN. My name is Rich Walls. I serve as the moderator for the summer lecture series today. So we are happy to have our colleagues over in Geneva, Switzerland, to talk about the CMS experiment. So uh, I don't have your names right there, but I'm going to pass this along to you all, and the show is yours. So thank you very much.
Great. Hello. So my name is Andres. I'm a member of the CMS collaboration and I've been working with the CMX experiment for a long time. I'm originally from Puerto Rico, and I went to grad school in the US, and I'm still affiliated with Tennessee Knoxville in the US, of course. Sonia?
Yes, okay, I wanted to give. Okay, my name is Sonia. I'm not a member of CMS, but I like to stay here. I come for another experiment that is, you just change one letter, is AMS, which is on the International Space Station, by the way. I'm an astroparticle physicist, and I'm here today to show you what we can see of the experiment. The person who will go underground. I'm ready, you see, prepared to go underground, and I hope that you will see through my eyes what we have here.
Uh,
Derek?
and I'm Derek. I'm Derek Grove. I'm a PhD student based here at CERN. I'm from the University of Kansas in the US. I've actually been to Fermilab quite a few times to do some test beams among some other shifts. But now I'm here doing in-person shifts at the actual experiment. It's a really awesome opportunity for graduate students to live here and be immersed in all the science. So happy to be here and excited to talk about CMS.
Okay, so we can get started. I think we have about an hour, I assume. So we'll try to keep this at around an hour. Um,
Maybe what I can do before I interrupt you. Okay, as I have to prepare to go down, I leave the floor. We will see in few moments on the other side. Bye.
Okay. So we'll give you guys an introduction. I'm not certain how much you guys already know about CMS, but we can just give you a bit of context and then we'll dive a bit into more detail. So perhaps we can share the screen just to give you some context. I think, I assume all you guys are familiar with the LHC in some way. And here you see a view of this giant yellow circle, which is obviously not painted along the ground. This is just a representation. So as you may already know, most of the LHC infrastructure is deep underground. So it's about 100 meters underground. I think at this point I'm more used to the metric system, so I apologize for the units. If you know the
I think I do know it in miles,
it's like,
but in kilometers, it's
Yeah.
27-kilometer circumference. So if you were to straighten it out into a straight line, that's how long it is. And then I think in miles, it's 16.8 miles.
16.8. Yeah.
So if you're driving on the highway and obeying the speed limit, if it were 60 miles an hour, that would take you about 17 minutes to drive the length of this collider, basically.
Yeah. So maybe just to give you a sense of scale, so I had a meeting just before this virtual visit, and most of our meetings are in the main campus, if you will. So it's where the most of the CERN facilities and offices are. And so that's here where the mouse is, and it's also next door to Atlas. So very convenient if you work in the Atlas collaboration. But I had to drive, and it takes me about 20 minutes to drive from the main campus to CMS, which is here on the left side. And you can see the lake, the Geneva Lake in the background. You also might see the airport where it says LHCb. And then the city of Geneva is just all around the lake. Yeah, so we have a few other experiments. As we said, the LHC is, yeah, I think, is it the largest experiment on Earth? I think it is. I think that's a
I think we can
accurate
claim that
experiment.
title, yeah.
Yeah. So should we move to, this is a sort of an abstract representation where you see at the top the large circle is the LHC, but we have uh, many other accelerators and many other experiments that are ongoing at CERN. So there's many other activities. You hear about the LHC a lot, but there's a lot of stuff going on at CERN. If you're curious about any of these things, we can, of course, elaborate.
But it's also the history here. There's
Yeah.
like a history to this picture. So like SPS was at one time, the largest collider. And they did a number of experiments, but the main one was, I believe, antiproton collisions. That was kind of the big deal for that accelerator. But every accelerator has an energy limit, which is related to the size of it. So that's why we keep building bigger ones. We need higher and higher energies. And you can kind of intuitively understand that energy limit if you imagine you're driving in your car and going around a roundabout, right? You can only go so fast around a roundabout before you're going to roll your car. You can't keep your car in the ring any longer. So there's a speed limit, and that's an energy limit. So it's the same thing for these accelerators. We have to keep building bigger ones if we want to go to higher and higher energies. But they inject into one another, which is kind of cool. So you start the beam in the smaller one, get it up to the limit, inject into the next one, get to that limit, and then into the LHC.
Yeah, it's almost like a stages of a rocket where you have a first stage to accelerate to a certain speed, and then you have more stages. So since you mentioned history, and since some of you guys are at Fermilab, I also wanted to mention, so the SPS was operational between the 70s and 80s, and we meaning the physicists at the time, discovered new particles there. So what we call the vector bosons were discovered, and there was a Nobel Prize awarded for this work. But I also wanted to mention later on in the US, Fermilab operated the Tevatron for many years. And in 1995, if I recall correctly, the discovery of the top work was simultaneously announced at Fermilab by the CDF and D0 collaborations. So a lot of history also at Fermilab, and you can consider the Tevatron the direct predecessor of the LHC. Also, interestingly, and sort of in parallel to the SPS, the Tevatron collided protons and antiprotons, which is also very fascinating. So maybe let's keep going, and I think at some point Sonia will be ready.
Yeah.
So a view of the underground areas. I kind of want to start talking about CMS. I don't know if you want to mention anything.
No.
Yeah.
CMS only.
CMS only. Well, now we have the slide where we have the other experiments. So we do have. I will say we have the Atlas experiment, which is sort of designed to do the same kind of science that we do with CMS. So in a sense, they're our competition. So we try to do our write up papers, which is a very elaborate and complicated year-long process. But we try to do, we try to produce better results while also being faster than an Atlas. That's in a nutshell our goals, let's say. And then Elise and LHCb do more dedicated analyses and physics. So Elise actually focuses on the heavy ion analysis. So actually at the LHC, we can collide protons together, but at certain times of the year, we can also collide heavy ions. So for example, we can take atoms of lead, strip all the electrons, and then we circulate the nuclei of these lead atoms, and then we can collide them. And that's super interesting. We can also do that, and we study this in CMS, and we also try to compete with the Elise collaboration on this. And then on the other hand, LHCb is looking at what we call flavor physics, and this has to do with like the matter-antimatter asymmetry, which we can discuss later if you're interested in. And again, CMS also participates and competes with LHCb. So we try to also participate in this kind of research, and yes, we're sort of competing on all three fronts, if you will, and many others.
I think CMS
Andres?
Yep.
Sorry, can I interrupt you? Because
Yes.
I lost you a certain moment. Okay. So just I wanted to comment something that you said, because we were talking about the Nobel Prize on SPS. Okay, I didn't mention I'm Italian. So one of the two Nobel Prizes assigned was an Italian physicist, Carlo Rubbia, and then the other one from Netherlands, Simon van der Meer for the machine. And then I profit here to show, but then you will have also on the screen one simulation of a collision. But what I have in my hand maybe is much more interesting, because this is a piece of the LHC. In particular, this is the beam pipe. Okay, don't be scared. It was never used, so it's not radioactive, so I'm safe. But as you can see, okay, I put my thumb. So you see the sides, the diameter of the cross section of this pipe that is quite big with respect to the cross section of a beam just before the collision. Let's say that the cross section of the beam, that is a very important parameter that we have to control before we collide particles, has a proper name. It's called emittance. And the emittance, the typical emittance that we have for the beam before the collision is a few tenths of microns, which means that is less than a human hair cross section. By the way, the cross section of the beam pipe is much larger, as you see. I don't stay now to explain everything. Maybe I can leave the floor to Andres and Derek as I go down. But maybe you can see the shape. Okay, this is metallic. Here we have a hole where you can see some coating inside. This is made to also, is not just to make it nice, but is used to, how to say, to capture all the protons that are not following the main path, the main flow of the beam inside the detector, because as you know, protons are all positive, so they tend to repel themselves, but we need to keep them all together. So I put this now back in this piece that is again not a simulation, is a real piece. The only thing that you don't have the proper path because it's cut. You see here what we call a dipole is an electromagnet. This part that you see here are cables. They are cut to show you how they are grouped around the beam pipe. And this is a dipole because you have two groups. You can recognize, you see here, there is a space and there is another one below. So you have one group here and one group here. I would say that if you look from the cross section is a sort of butterfly. This object, you have one beam pipe here, one beam pipe on the other side. And these cables, they go all along, as you see here, you have the bottom part all along the beam pipe. You should imagine that you have another part here on the top. And they follow the 13 meters length of this object inside the LHC. These objects, we have 1,232 of this as a sort of big Lego that you have to make our accelerator and the collider. They are there to bend the trajectory of the particles, because otherwise, if you don't do anything, the particles, they go straight forward. But we have a ring, so we need to bend the particles all around, and this is why we have these objects. I repeat, it's a big Lego. We have also other objects. Maybe if we will have time, we'll talk about this. But just to mention, we have objects to give energy to the particles, objects to bend the trajectory of the particles, objects to focus the beam. That means to squeeze the beam, to reduce the distance among all the protons inside the beam pipe before the collision, just to reach, as I said before, the few tenths of microns before the collision. Now, I will go on the other side. I take for just another moment the floor just to enter. If you follow me, I'm in front of a door. This door is called pad, is for people to enter inside the experimental area. Is not the underground area, it's still the surface area, but is already the experimental one. To enter this door, I need to pass 3 checks. One check is to step in maybe Noemi can show. We have a sort of square there. You can see maybe the yellow dots here. So I step in. There is a sort of scale. I'm not, it's like I cannot see my weight, but the system realizes I'm a person. And then I cannot enter with any object, for example, a backpack, or just not wearing my helmet, for example, keeping my helmet in my hands, because there are infrared beams that are checking that I have nothing, you see. I have just this small bag, but I will cheat the system just saying like that. And then the third one, the most important, is the iris check. So I have to read my iris, the biometrical check, in a system here to be recognized as Sonia, okay? So I will show you, first of all, to open the doors, I will use my personal dosimeter. You could ask yourself, but this is already personal, but somebody can steal this from me. So this is why I also need the biometrical check. So I try to make myself recognized. It's okay. And then now I step in. Hopefully the door will close. That's it. And now what I do is the biometrical check. They take a photo and I'm passed. And now the same will be done by Noemi, that she's with me. She's managing the broadcasting of the images, the stream. And so she's much better than me in passing objects, because you can imagine she has things with her. And in fact, the system is complaining. So we have to wait just a moment for her to pass again, because as I said, the infrared beams, they are preventing people to bring inside objects. So we need to be much clever than the system itself. Now it's okay, she's in. She will do the biometrical test. And then I will wait for her to bring you, yes, perfect, to bring you inside the experimental area on surface. If you follow me, you see that we have other doors here for people, other 2 entries here. Now they are not used, so we can enter both sides. And you could ask yourself, how do you do if you need to bring materials? We have another special door here. And this door, basically it works in that way. There are 2 doors, maybe you can see here from the pictures. So we open the doors on the opposite side, so from outside, we leave the material inside, and then we badge through the green doors that you already saw, as we did, and then we open this one, the door that we have here. Now, the elevator here that fits almost 40 people inside, if we need, is now at minus 97 meters. We just call the elevator. We ask the elevator to come up, and okay, we wait a little bit. I give the floor to Andres and Derek, and then okay, I will just take the floor before going down again. Is it okay? Is it fine with you?
Okay, so Sonia will take over, because I think you will freeze at some point.
No, actually we didn't lose it.
Okay.
Oh yeah, she
was it okay?
Right.
Was it okay?
Yeah, so far it's okay, but
Yeah.
we did want to take a chance to talk about the CMS detector, if it's okay.
Yeah, the only thing I want just to show now the elevator is almost here. If you just give me a few seconds, we have 10 meters for the doors opening. And then I will show as I'm in, and then I will give you the floor. Okay,
good.
This is the elevator. As you see, I blocked the doors. Noemi is coming inside. So you see, level 0, we will lose the connection as I go down. We have 3 levels. 0 is surface, -1 about minus 80 meters, -2 about minus 90, and -3, as you have seen, maybe minus 97, minus 100. So we will go to -2 now. And okay, we will broadcast as we can how deep we go. And I leave the floor to Derek for CMS. Bye.
All right, so I think we just lost Sonia. So we want to take the chance to just quickly two things. So to mention again to people that joined just more recently, please feel free to ask questions, but please use the Q&A. So you can just click on the Q&A and send us any questions you have. And you're encouraged to do that, of course. We'll just address these questions when we have some time. And then we also wanted to show you guys a little bit of what CMS looks like. Unfortunately, we have collisions at the moment, and we cannot show you
That's fortunate.
Well, it's fortunate, although it's not stable beams, it's just loss map. So it'll be, okay, in a few days, we will have physics, what we call physics. So we have stable beams, and we're collecting good data for analysis. But in any case, we wanted to show you what the CMS detector looks like, and I think we can share the screen here. So of course, here you can imagine that the protons are coming in and they collide in the very center of our detector. And of course, the detector is not open like this, is just to show you the inside of our systems. And maybe to be as quick as possible, so working our way from the outside in, you see that there are these layers where you see all the red these are not modules. The red is actually steel, but it's interleaved with these modules that are sort of silver looking. So all of that corresponds to the muon system. And muons are particles that are similar to electrons, but they're a lot heavier, so about 200 times heavier. And without going into too much detail, they're very important for us. So it's part of CMS, the name, right? Compact muon solenoid. And so we can discuss a bit more, but just to be brief, I'll go on to the next layer. So the next layer is this cylinder, and it just looks white, and it's a cylinder that's 6 meters in inner diameter. That's our magnet. So it's a superconducting magnet, which generates a very large magnetic field. So it's 3.8 Tesla. So it's on the order of 100,000 times larger than the Earth's magnetic field. And again, we can discuss the magnet in more detail in a bit, but just moving in, then we have the calorimeters. So we have two types of calorimeters. We have the hadronic calorimeter that it helps us detect particles that are made of quarks. So just like protons and neutrons, but there's many other types of particles that are made up of quarks. And then moving in even closer, we have the electromagnetic calorimeter. And there we detect particles such as protons or electrons or anti-electrons, and also photons. So photons will interact with the material, and we can also detect them. And finally, the innermost layer, again, very briefly, we can go into more detail, but the innermost layer is our tracking detector, and it's made up of many, many layers of silicon sensors. And then these help us measure charged particles. So we basically see a signal in each of these sensors, which is a bit like a camera sensor. And then we connect the dots to look at the trajectory of the charged particles. So that's the shortest I can make this. We also have this slide, but I want to check with Sonia just in case she wants to.
Exactly.
Yes.
Yes,
Okay,
okay. I was carefully listening your description. I can say without watching the slides, I was able to understand everything. So I'm here now. I stepped out from the elevator. Noemi, she's showing you the doors, the green doors of the elevator, and then I'm just in front of the elevator. I want just to spend 30 seconds, if I can, in this room, because this is very important. You know, one of the, I would say the most important thing when you are doing experiments, and not only experiments, is the safety. And here, really, you can leave the safety. Why? Because this room, in case, for example, of an evacuation alarm, is the place where we can wait the elevator and reach the surface using the elevator, because the stairs, we have stairs, but they are strictly forbidden. Also because we are more or less at minus 90 meters, which means that if you want to reach the surface, you know, one floor is more or less 3 meters. So we are more or less 30 floors down. So it's not easy, even if you are trained a lot. So we must respect this rule. We must evacuate using the elevator, but in case there is a power cut and the elevator doesn't work, we can safely wait here. We have many things to wait here. First of all, because the air is pumped outside, which means that is an overpressurized area. So nothing can enter from the outside. I mean, smoke, for example, if there is a fire or if we have a gas leakage, because we use gases for the detector, and so they keep the place of the oxygen, so we can have a phenomenon of asphyxia. So here we are safe because this gas cannot enter. And then, okay, we have I call it the big brother, is from the control room. We are followed by our colleagues from the control room. And then if we want to talk with the fireman, we have this nice red phone. We just need to lift this up, and there is somebody on the other side, is a fireman who knows perfectly where this phone is installed, and okay, ask us what is going on. So we are, and then we have mobile phones, other things. So this is the safest place. But I would say that everywhere is safe because we have so many detectors to prevent any problem that, or to just to tell us that there is a problem, that I would say that it's much safer to stay here than on surface, because we could have a piece of, I don't know, a satellite or a meteorite coming on the ground. So here is really safe. Now I bring you inside the real service cavern and the real, I would say, experimental area. Now we are in what is called the service cavern. I know that there is a nice slide to show, but okay, just follow my hands also. So we have two caverns in that way. I put in front of you, okay, in that way. This one on the left is the service cavern where I am. And this one is the experimental cavern. The service cavern, as you see, is longer and thinner, while the experimental one, let's say, is shorter and a little bit larger. The experimental cavern is on this side, as you can see from the picture. Maybe you can see, I don't know, a gray wall made of blocks. They are not, they are all glued together. However, this is a prism that is filling a corridor. And if you see the mechanism, the yellow mechanism, when we pull this mechanism back, we can open this corridor. And this corridor is the connection between the service cavern and the experimental cavern. When we open this, of course, when there is no physics as it is now. And maybe I can ask also Noemi if she could show us the surface, just to show you that I'm really underground, I'm not cheating. Maybe you can see some light, a sort of light square, a little bit lighter than the rest on the top. And this is the surface where I was just a few minutes ago. And you can understand that this shaft, as it is called, is used to bring up and down material and then to introduce the material through this corridor I was talking about before into the experimental cavern. I'm in the middle of the service cavern, and now I will bring you with me to the first room where we have electronics. This is not the only room where there is electronics. There is another one that I would call a twin room on the upstairs here, and then we have other electronics on the other side of the service cavern. That more or less is the sum of the two here. And this is, let's say, is giving the lower level, if you want, of the brain of the detector. Because electronics is the brain of the detector. We have some electronics inside the cavern, just attached to the detector. And then we have a level of electronics outside here. And the next level, which is the higher level, it's on surface. I will leave to comment this part to Andres and Derek, because this room, if you cannot hear, but is already noisy, but inside is even more for me. So it's really hard to talk. Times to times I will jump in, and Andres he knows, just to show you some optical fibers, there are some cables. Take a look and consider that we are going in places where normally visitors cannot go. So you get the chance through this virtual visit to see places that are not allowed to be reached by visitors when they come here in presence. Okay, Andres, it's up to you, Andres and Derek, to describe the part here. I leave you the floor.
Okay, thank you, Sonia. And so there might be a few things that we would like to show. But I also want to mention a few things. So first of all, we're taking you to a forbidden area for visitors. So, you know, you have the chance to look at some of the systems that only the experts have access to when we're debugging the system or replacing components. And you can see here parts, I think these correspond to the tracking detector. There's a lot of fiber optics. So most of the cables that you see here are fiber optics. We actually read out most of the data from our detectors via fiber optics, so we get optical signals. This is part of the data acquisition system where we sort of combine all the data from the different systems. You can see how neat the cable management is, which is something that's really, for such a complicated system, it is, of course, it's important to keep good cable management, but also very challenging to accomplish this. So it's really it speaks to the attention to detail, right? So there's a lot of this kind of infrastructure. I mentioned a few systems. The tracker I referred to before, where we have the silicon sensors. So we're getting data from these silicon sensors, and that data is encoded into optical signals, and it goes into these modules. I don't know if you're familiar with FPGAs, which are field programmable gate arrays, but essentially it's like a chip that you can program on the fly, and you can change the programming. I do want to mention the trigger, but first I wanted to ask if Sonia, I think it's in this specific aisle.
Yes, Andres. Yes, Andres. Yeah.
So
no, I was following what you were saying, and you were mentioning that cables. Okay, here is a little bit messy with respect to the previous one. Sometimes we cannot do so precise, but of course we try really to arrange cables in such a way that we can recognize. For example, I don't know if it's possible to see that each cable has a label, and then I have my preferred wall. Maybe we can go quickly there. That is related to the system you were describing before. That is the muon chamber. They say the system that is in the edge of the detector, and this is the wall that I like the most. Is this one? Let me, I don't know if there is any interested in art, but okay, let me say that for me, this is the
Sonia,
Mona
Noemi,
Lisa of cabling.
Please be very careful. High voltage is on.
Yeah, we are very careful because, you know, in those cables, we have 12,000 volts flowing in. So it's, I repeat, 12,000 volts. So it's really dangerous. So we pay attention, but despite this, that we'll be careful. Just have a look to how these how these cables are organized, are labeled. Consider that each cable has its own length, and that must be let's say routed in such a way that you respect the bend of the cable. They cannot be let's say pulled too much or stretched, otherwise you can break the connectors. So there is a technique. It's not just to put the cable in the connector. And then, of course, there is also a process that you have to do before. That is what we call the mapping
which means which cable should stay in a specific place on a specific connectors. Maybe I feel in that way because I did some cabling for AMS for the optical fibers, and I know how much work is here. You are really happy if you can just do half of this wall in one day, and when at the end of the day you push the button on and everything works, you say, okay, I did my job today. So really, we are proud when we do these kind of things. Now, I go down. I don't know, Andres, if you want to continue with other things, and I wait for
actually,
you
Sonia,
in front of the red door.
Wait, Sonia, actually, would it be okay
Yeah.
to show one of the aisles? So we actually want to show the pixel feds, and I think there's a barrier.
Feds. Yeah, yeah, there is a barrier. This is why, as I said, for the safety, usually we do not overcome barriers, but we have a special permission.
Yeah, so okay, we wanted to show you this, and I'll let Derek talk about this.
Yeah, so
yes, Derek.
Some of the work I do here is with these pixel feds, or rather just with Pixel in general. So Pixel is a subsystem. We briefly went over that picture that shows Tracker, eCal, all the other pieces of CMS. Inside Tracker is the pixels. They're very, very, very crucial for getting the track information from these collisions. These pixel feds, fed stands for front end driver, I believe. Yeah. The signals coming out of Pixel come to these feds, and you can see there's yellow cables. I'm honestly not sure what those are, but the cyan cables are fiber optics. And so a lot of these machines or these boards in this room have these fiber optics cables coming in, and that's usually signal from some detector. But what I wanted to mention is just to kind of give you a sense of what it's like to work on an experiment here, or work on a subsystem. Like, there's experts working on each of these subsystems. For the pixels, you know, we're up here in the control room, and if something goes wrong, we have to fix it as quickly as possible. And to show an example, so you see the feds there, all the lights are on, which is great. But one day on shift, you know, one of them went out, or there was a problem with one. We didn't really know what was going on. And so we have to physically go down there and try to debug this in real time, troubleshoot, figure it out. And so maybe we can show, I took a picture from when we were on shift, but basically we go down and we don't know which one has the issue, right? We just know there is a problem. So we're looking around, and then we see something like this. We'll transition to the picture. So on the right, yeah, basically, you know, which one of these feds has a problem. You can try to guess yourself. So this is just what it's like to work on these subsystems day to day. Yeah, there's going to be problems, and you have to be the expert that goes and figures it out. So in this case, it was clearly that fed. We tried to manually reset it, didn't work. We had to pull it out, put a new one in, and then program it and get it all running within like a couple hours so that we could get back to taking physics data and running the entire experiment. So there's a lot of people running around working on their subsystem in real time, and that's just kind of what it's like to be here. Very cool.
And Derek, can you hear me?
Yes.
Yeah, and okay, just to say more about what you were just saying, I remember when, okay, in my first part, I was not babysitting the electronics, but some colleagues of mine, they were, and they were doing exactly what you were mentioning. And sometimes, even when they identified the board, so the module that was not working, they tried to replace the module, and it didn't work at all. And at the very end, they after, you know, 2 hours, as you said, 3 hours without having nothing, no results, they reinstalled the previous module, the one that in principle was showing up the problem, and it was working. It was just because it was too hot a certain moment that it was not working 2 hours before. So you are really, as you said, that to manage to go there to figure out what is going on. It takes time time, and I would say also passion, because you want that your experiment works properly to take data. I'm here to show this red door. There should be, I guess, a slide that shows the path. Otherwise, I have is the one that you saw before. So I cannot open this door because it's sealed. You see, but you can imagine that here there is a corridor, and this corridor brings to the LHC tunnel. Now, this door has not been installed here because we want to go to the LHC, because people working to the LHC, they go using other accesses. And also CMS people, they don't want to go to the LHC. They want to enter on this other side that is another corridor that connects the service cavern, where I am, to the experimental cavern. So why this door? Because if we open it, there is after a few meters, another elevator. So as you see here, well indicated, this is a second escape, let's say, path, emergency path that we can use in case we can. Okay, I just do the last part of my, let's say, because we are almost to the end of this tour underground, and then I will leave the floor upstairs. So I have a few things to show you. The first thing is to check if we have a magnetic field, because my colleagues on surface, they told me that there is a magnetic field, but I'm not confident. I want to check by myself. You know, a physicist usually wants to check by himself or herself. So I have here, you see, a very special and scientific object to detect magnetic fields. Sorry, because I unmounted it. It was in my pocket. You see, maybe you can recognize. Is a chain of clips. Okay, and you see, this is not magnetized at all. You see. So now let's check if I can detect any effect of the magnetic field inside. I remember that it was said that the superconducting magnet inside the detector in the center delivers a magnetic field of 3.8 Tesla. Here we just should feel a fringe magnetic field that is not dangerous for us. So I can go, let's see, just point this last clip of the chain. Let's see if something happens. Okay, I go slowly. Let's see. I think that something starts to happen. As you see here, I see something bending. As you see, this is not me. It's not. I'm not becoming magnetic. As you see, I would say that I can detect something, and this is the magnetic field. But then, okay, I have to say that my colleagues, they know that I get lost in this moment. So forgive me. I will start to play just to enjoy myself, but I hope that you will enjoy too. So for example, doing this, okay? Or just to satisfy my big ego, as all physicists, you know, they have a very big magnetic ego. This is S for Sonia, okay? Or maybe we can do another thing. You know, this wall is no magnetic wall. Consider that the detector is just on the back, more or less 20 meters, I don't know, something like that, to the middle, something like that. I never measured. Yeah.
Something else is that this wall that separates you from the detector is about 7 meters thick of reinforced concrete. So
yes, exactly.
The magnetic field is much stronger inside.
Yes, of course. We have the chance sometimes to enter inside. Is I would say magnetic resonance that we take, but it's okay. So you see my chain. What I wanted to say, that the screws, they are magnetic, even if the rest is not. So you see, I can attach my chain and maybe just do a pendulum, or This is a mess that happened to me once I wanted to do this. It happened that also the other clip attached. And so I decided to name this new object the magnetic swing. And you see here, basically, I get an elastic force coming up, which is bringing up the chain. I can really feel, believe me, the force, the elastic force pushing my fingers up. And this is because, of course, we have the gravity that would like to keep down the chain and also the magnetic field acting here. In fact, this chain that seems to be just, how to say, a funny thing, once made me able to understand that the magnetic field was off, was weaker. Why? Because I couldn't do this. It was falling down. So I had to remove some clips and to attach again. And then it worked. So I went to the control room asking the shifter why, if there was any problem with the magnetic field. And they answered yes, because this morning, this was in the afternoon, we had a problem. So we decided to run with a weaker magnetic field. So you see, a chain of clips can made me able to understand what was going on inside. If I could calibrate, so to number how many clips for the magnetic field inside, I could even have a rough measurement of the magnetic field. But okay, I always ask for this thing, but for the time being, I didn't had the chance to calibrate my chain. Other few things, and then I will leave the floor again to the surface. So I have one thing that I would like you to show is that this one. I don't know if this works. So let's see. Maybe yes. Does it work? Yes. Look, these clips, these are colored. You see? But you see that they move alone. This is because they are, you see there how they move? This is because they magnetize. And then we can also do another thing, which is this one. Look here. Maybe you can see, is also on the floor, is also here, you see? And this happened when I was looking for my chain of clips. I couldn't find, so I took all the clips out from this small bag, and they landed on the floor in that way. So I will show you. This doesn't work. It's not a problem. You see here, they attach now. Let's do in that way. I wanted just to show you that if I stop them, you see, I try to move just doing some wind, they do not move. But if I use this chain, you see, this clip, you see, look here. Again, they magnetize and can move using, and then I can also, you see, collect them quite easily. In that way, you see, very nice, okay? And then I can use this object again as a probe of the magnetic field, because you see here, the magnetic field is enough to keep all the clips together, but if I move, I don't know now I will do, you see, they fall down. Why? Because here the magnetic field is weaker. How can I understand this? Also because you see, I show you another thing. This you should recognize. Okay, just to see that is a live transmission. This is my mobile phone with the time. You see, I have a compass here. So you know that the clip aligns to the magnetic field lines. And so you see, this is the magnetic field. And of course, you have a changes in direction and also a change in intensity, as you have seen before. So you see that with the clips, you can really do a lot of things. The last thing that I will do, and then I give the floor, promise, is the last thing that we have is this duct, you see? Now, my colleagues, they were talking about the shifters. You know, we have this, let's say that doing a shift is 8 hours babysitting the detector. Sometimes it's stressful, can be funny, sometimes not. So sometimes there are not too many volunteers. So I know that these years, every person who is doing a shift put a duck inside a big box with the name, just to see how many people are doing the shifts, and then who did more shift will get I don't know, a prize or something. So this duck, I put a clip, you see? I put a clip here. If I would have been inside the cavern, keeping this duck in that way and approaching the detector, you would have seen the duck flying. Andres did with me, he knows, it's really a weird thing. But here, as you see, the weight of this duck is too much. But so I guess that you know Batman, the cartoon. So let's do the bat duck here, which is just this one. So this is my bat duck. And with the bat duck enjoying here, I think that as I cannot move from this place because I cannot enter the cavern because of the door there that Noemi will show you, I leave the floor to my colleagues, and I will meet you again on surface.
Okay, thank you, Sonia. We also wanted to, so we are running a bit low on time. So I wanted to stress again to please ask questions in the Q&A. We're happy to answer any questions that you may have. But also we wanted to talk a little bit about what's in the horizon, what's coming up next. So as you may know already, we have been running the LHC since more or less 2010. And what you may or may not know is we run the LHC for a couple of years and then we take a break. Everybody goes on holiday for like a year or so. It's very relaxing. Of course, that's a lie. We actually work really hard for a few years, so a year or two, and we upgrade certain parts of the detector. And so we ran from 2015 to 2018, and then we since 2019 to 2021, we were upgrading a lot of our detector, and the LHC made many upgrades. So we have been running since 2022, and we will stop running in the middle of 2026 next year. And then we will have a lengthy shutdown period because we will come back in 2030 with a very major upgrade. And for this upgrade, we will actually we have a different name for the LHC even. We call it the high luminosity LHC. And that's because we will dramatically increase the rate of collisions or the rate of interactions when we make these collisions. So in current conditions, we have hundreds of billions of protons that get very close together, and about 60 of them will actually interact. And I don't know if that sounds impressive to you, but it should, because that's cutting edge, that's state of the art, that's the best humans can do at the moment. But for the high luminosity,
it's a billion collisions a second usually.
Yeah,
right?
that's the thing, is we're doing that process about 40 million times per second. Let me share the screen too. So you have here a simulation of what this looks like. So all these green lines are the trajectories of particles that are scattered when the collisions happen. And each of these yellow dots is at a point at which one of these or a pair of these hundreds of billions of protons are actually interacting. And so every time we cross the protons, which again happens as often as 40 million times per second, we will have about 60 of them interact. And we will be working, and we have been working for many years now, on upgrading the LHC and upgrading the CMS detector to take that to 200 or more interactions per crossing. And that requires, building brand new detectors. So we talked about the innermost detector of CMS, and that alone will be, I think, the innermost detector, which we talked about. That alone is an extremely complicated project, and it's not just building or it's not just replacing the detector, it's upgrading it. So there's many more capabilities that this detector will have. Without going into details, we actually never talked about the trigger, so you can ask us about the trigger if you like. But that's one of the new capabilities. And then we will also have, I try to find a picture here, but I didn't do very well. So I'm trying to get a good photo of HGCal. Sorry, I'm trying to get the cookies. So here you can see a picture of CMS when it's opened up, which we also didn't really talk about. So CMS is very modular, and we can open it up. It's a sort of a series of wheels or slices, as we call them. And we have this end cap slice, which has the end cap calorimeter, and this entire thing here fits inside the magnet. So in a year's time or so, we will remove this entire thing and replace it again with an upgraded detector. And you can see a sort of representation of what it will look like, the different layers on it. But I wanted to stress that these are two of the major projects for CMS. The inner detector, the silicon sensors, and then this end cap calorimeter. And I would argue, I'm not an expert on I think Sonia might be more of an expert on satellites and the technology that goes into it and the complexity. But I would argue that each of these projects is on the order of complexity of building a satellite, a very complicated satellite, I would even say. So
Andres?
that's what's in the horizon. So yeah, you have anything to add?
Yes, you called me because I heard my name.
Yeah, so
you were calling me?
Yeah, so I was saying that the new upgrade projects such as HGCal or the next generation inner detector, the tracker, is as complicated as building a satellite. And I was saying that you might have some insight into how complicated a satellite is. So it's a different kind of project, but I think in terms of complexity is comparable.
Yes, of course. No. Yeah, I'm in the control room in any case. Yes, okay, that said that the main complexity going in space is that you need to add some tests that usually on surface on the ground you do not add because you are in the vacuum. And if you are, of course, orbiting around the Earth, you experience sunny periods and shadow periods. So these are added let's say, tests that you do. You have to do vibration tests because of the engines of the rockets that you are using. Concerning the complexity, yes, but okay, I would say it's comparable. It is, as you said, is not more. The only thing that you need to put much more tests before you bring something outside the Earth. Maybe you need also a cooling system. Okay, just quickly, we want to comment. Just okay, here we have what we call the technical side of the control room, which takes care about the safety, the infrastructure, and the powering, etc. Then here we have the shift leader, so is the commander, the pilot of the crew here. And then here we have the data acquisition corner, which takes care to check if the data acquisition, so we get data in a good way. And here then we have the corner of the trigger. I don't know if you had the chance to know. Okay, I will leave you to say something maybe about the trigger, etc. Maybe I will just add, and then I will stop myself. I would like to add that, okay, to my experience, not being a member of CMS, this is a very user-friendly control room. I like a lot. I know that there is a tradition of, I don't know if it's still there, that the shift leader sometimes in the morning comes bringing the croissant to the whole crew. In AMS, you see, you just change a letter. This is strictly forbidden. In the control room of AMS, even a bottle of water is not allowed. If you want to drink, you go outside the control room. If you cannot go outside the control room, you wait to drink or to do whatever you can imagine you would need in your life as a person. You just wait. Okay, if you want to add other things, I stop myself, I remove all my stuff.
Okay, so I did want to go over a question that we had. So we have only gotten one question. I think we have time if you want to ask a last minute question, but we have Dominic asking, how safe is the magnetic field? And Sonia mentioned that we sometimes get a chance to go into the detector, and some of our colleagues go inside the experimental cavern to do some kind of work while the magnet is on. And so the magnetic fields that we would be exposed to is okay. So let me put it this way. So inside our magnet, we can generate up to 3.8 Tesla, which is I don't know if you're familiar with that unit, but let's pretend you are, at least for the time being.
I think the Earth's magnetic field is like millitesla.
Yeah.
Yeah.
So.
And so something to keep in mind is that I mentioned before that we have red layers in our detector, and these are stainless steel. And the reason for them is actually to channel or to compress, or I don't know how exactly to put it without getting technical, but it's to make sure we have enough magnetic field. It's to concentrate the field lines, if you will, so that we can generate 2 Tesla outside of the magnet. But this is still constrained to the physical detector. So once you're outside the detector, the magnetic field line drops off quite a bit. So all that said, it is perfectly safe. In order for and maybe a different way to put this is there are medical applications. So when you are getting some kind of a scan, medical scan, you might be exposed to on the order of 8 Tesla or so, and that is still perfectly safe. You really have to go to much higher magnetic fields, I think on the order of 20 Tesla or something like that, for it to have any impact on the body.
And also, this is a permanent, is a static magnetic field. If it would have been a variable magnetic field, it would have been dangerous. In any case, we went both. Inside the cavern, you see, he got curly hairs, and I am as I am.
It happened immediately.
You are still safe.
Yeah.
Once you go in, you'll get curly hair.
We no, but it's safe, enough safe. We get a lot of fun going inside.
Okay, so do we have any other questions? Anything? Maybe that looks like another question, or is that the same?
Yes, we have one.
Okay.
Yeah, most of the folks are on the on the live stream over here, so I don't think they had access to the Q&A portion.
Okay.
I do have my laptop over here if someone does have a question.
Well, if you do have a question from the crowd, and if we have time, we can try to answer it.
Is 10 more minutes appropriate? Unless people have to go, that's fine.
And with us,
yeah, we'll give you about 10 more minutes, and then I'll pass the mic around if people do have questions. How does that sound?
Sounds good. So we do have another question in the QA in the meantime, which I don't think I know the answer exactly. So the question is there any place in the universe where, so this is an anonymous attendee asking if there's a place in the universe where the magnetic field is of this magnitude occurs naturally?
Oh, sure.
So
sure. Even many orders of magnitude higher in neutron stars, and also even in that subset of the neutron stars called magnetars. It is billion times more than what we can produce. Indeed, this is not an extremely huge magnetic field. On the Earth, there are some test magnets where I think we could go up to even to probably 100 Tesla, a much smaller volume, of course, but the 3.8 is not extremely high. Even the 9 point something that we have in the accelerator dipoles is something not extremely high. The extremely high is the magnetars.
I was going to say on Earth.
There are 2 DQN alarms. Check plots in the DQN.
Sorry, we're getting a lot of alarms
Yes.
at the moment.
Oh, that's
Yeah.
a normal thing.
Yes.
Indeed.
We have also music.
Yeah.
Maybe
But even on Earth, I think a magnetic field is produced when you have a very fast moving current. And so sometimes that happens on Earth, for example, lightning. So I can't tell you that I've ever measured the magnetic field produced from a bolt of lightning. But I'm sure when it strikes something metal, if you were close enough to that piece of metal, and if there was enough current through it, you might get, for a brief moment of time, a magnetic field that strong. So you can kind of imagine yourself when you might have that, or if there's a high voltage system somewhere, maybe a power plant, and they screw up. There's many ways to produce a magnetic field that strong. This isn't, it's a very strong magnetic field, but it's still a natural magnetic field. You can create magnetic fields of any strength if you have enough.
And I would like to add, that this is the reason why we do astroparticle physics, because at a certain point you realize that what you can get in the universe is the scale is much, much larger. Energy, magnetic fields. Frankly, if I should be honest, and I guess that all my colleagues agrees with me, we are microbes with respect to what you can find in the universe.
Yeah, negligible.
The only thing is that here we are doing our own cooking. We have a machine that is the most powerful machine we succeeded with our technology to build up to now. And so we know what we put in our mixer, and we can guess using theories, models, what we can get out. Of course, we are looking always for the anomaly because this is the discovery, but however, this is when you go in space, for example, you detect particles, you don't know the initial state. But you know that the particles you are detecting are much, much more energetic. They have been submitted to higher, very intense magnetic fields. And this is why you have a sort of synergy to answer the same question from astroparticle and the particle physics on accelerators. This is the reason why.
Actually, I would like to emphasize what you said. One might have a question that if the universe is so much bigger in any sense, what we call energy, magnetic field, whatsoever, why do we invest money here on the Earth for the accelerator? This is the reason. So here on the Earth, we might have even these low energetic particles in a very, very large abundance. We can control the phenomenon. However, in space, we might have much higher energy particles, for example, but uncontrolled. So that's the two things that, anyway, we think that should go hand in hand, but none of them can exclude the other.
I know, exactly. It's the same, if we want to go wider, sometimes we claim that experimentalists, they are better or worse than theoretical physicists. This is not the case. There is a synergy, because sometimes it's the theory driving us to the discovery, and sometimes we do experiments and we find the anomaly, and the theoretical physicists, they have to correct the model. So it's a synergy.
In fact, I would even say that's all we do, right? We need the theory because all that we do is we have an expectation from the theory, from our understanding, from our description of the universe, and that is what we use to compare our experimental results with, right? So we need the theory to compare with our experiment, and we are constantly testing the theory. We're trying to find something unexpected, and that's how we make progress. That's how we find new phenomena, right? So another way to put this is, if your experimental result does not agree with your theoretical expectation, then one of the two is wrong. And if and that's how you make progress, right?
But it's not going to be the experiment unless your machine's screwed.
Unless your machine is
You
correct.
always
Yes,
trust
exactly.
nature's results over what you can write down on a piece of paper.
Exactly.
So,
But
yeah.
even when you make an experiment, there's always an uncertainty, right? You can only be so confident about your result. So yeah, there's a lot more to this conversation, but yeah, I think you hopefully you get the point that it's both are extremely important.
But this is the most exciting part of this job.
Mhm.
So we have one more question, which I think is really a nice question from Ryan. So he says, as a teacher new to particle physics, what's one concept you think is the most important and exciting to get across to students first? And he says he teaches mostly ninth graders.
Hmm.
So
Think for a moment. Yeah.
okay,
Okay.
I can start.
Yes,
I
start,
would
because-
say that what we do is extremely I don't know, it's driven by a very basic curiosity. You know, it's really we're driven by what is the world made of fundamentally, right? So it's really about what are things made of, and you say, well, okay, this is made of atoms, and for us that's not enough. We want to know, well, how do these what are these atoms made of? And we say, well, electrons and protons, and then we want to know more. We want to know what's inside of the proton and how does it interact with other particles, what other particles exist in the universe, and how does that relate to the early universe. So I think that to me it's just that curiosity is there in every person on earth, in my opinion. You just have to know how to sell it, you know, how to be like, well, look, I mean, what we're trying to investigate is just the most fundamental things, right? What are things made of? Or, you know, you can connect it in many different ways, but I think you can always sort of latch on to that curiosity that I think every person has.
I have one more. I remember when we exactly in the ninth grade, when we started physics, what was the first topic that we faced? And that was something that I think would be extremely important in the society to understand, that we are making models only. The concepts that we are using in physics, wave, particle, whatsoever, are models to describe the reality, but the reality is something completely different. Probably we won't have probably the possibility to understand. We always use models, we always use resemblances, just like in the literature, for example, to try to understand how it works. And what is important in these models, that these models behave accordingly to the requirements of science. So the model is not just a story that we tell about the universe, but the model you can always make calculations within the model. You can make predictions in the model that you can then check with your experiments. And I think this is the biggest concept of physics, that we don't know how it works. We have an idea to describe and actually necessarily partially describe the phenomenon. And if we can describe one phenomenon with a model, we can make a prediction and we can check this prediction. And if the check is positive, then we can accept this model as a working model. But no one of us claims that the world is like that.
Exactly. I really dislike this, you know, talking about laws of physics. All we have are models, and all of them are temporary. You can take this to the extreme and say, well, tomorrow the laws of physics could be different, right? And that's how science is, right? We just constantly try to further our understanding, and as I kind of mentioned before, our jobs are to challenge what otherwise might be called laws of physics, to test them, and that's what it makes us, but what motivates us, right, to find
Exactly.
something unexpected, something that challenges or is different, or in contradiction to these established, established models, let's say.
Exactly. And that's why sometimes we operate with extremely weird objects, wave functions, Calabi-Yau shapes, etc. That that is very weird to the normal human being. But we know that these are models that might describe, at least mathematically, what is happening.
I can give a very real suggestion to Ryan. We did a lab in undergrad. I would suggest maybe trying to adapt this to your lessons, but it's a lesson on models. Ryan, right?
Yeah.
It's a good question. And I'm glad you're wondering how to inspire younger scientists. This experiment or lesson on models, physical models, our professor took a box, he put something in it, say, I'll give some answers away, a golf ball, a dice or die, I guess, or maybe a pair of dice, all this stuff. And then you tape it shut like crazy. And then you give that to the student and you tell them they're allowed to interact with the box and they can do a number of experiments. They can rotate it slightly. They could take a magnet to it. They could do these different things. And they need to try to figure out what is inside the box. And that's a very, very good lesson on how we develop these models in physics. And then the key thing is at the end of it, don't tell them what's in the box. They're not allowed to know. They can get very close to knowing what's in the box. They'll probably figure it out. But the golf ball seems a lot like a regular ball unless you do a very slight tilt and it doesn't move. If it's a perfect sphere, it would roll at just about any angle. So
I had
think
an
that's
exam like that at
Yeah.
university. It was called the black box
Yeah.
exercise with the electrical things
Yeah.
to check, to understand which one, which kind of circuit was inside, you know, just measuring different things.
But it makes a good impression
Yeah,
because
exactly.
that's all of science is
Yep.
you do
And
experiments and you
especially the
make a
part at
model.
the end,
Yeah.
you don't always get the answer in science, right? So
Yes,
Mhm.
exactly, because
You don't know.
you don't
Yeah.
know.
So these particles, a lot of the theory describes them as a very bizarre thing in quantum mechanics and with waves, but that's the type of math that describes their behavior. And so when you're online, I'm also now warning you, when you're online and listening on TikTok and all this stuff, and there's people talking about, I don't know, quantum immortality or all this stuff, like it's very bizarre. That's not exactly what's going on. The actual physics is this is the math that explains the experiment. And that's also the model. The math is the model. So I think that's kind of what we're
If
touching
I
on.
can go in another level that is even more basic, I would say that, of course, one ingredient is curiosity, as you were saying, Andres, of course. And basically, to me, I think that to be a researcher, I don't like to be a scientist. It's too much scientist, you know. To be a researcher is exactly the right meaning of what we are doing. By definition, when you are a researcher, you don't know the answer. And so this is the most exciting moment because you are in front of a problem, you have to solve this problem. And as we do in the daily life, so I think that students, they should understand that they are solving a lot of problems in the daily life. They don't think, for example, that they are using math because it's just automatic. For example, when they cross a road, they are estimating the speed of a car coming and the length of the road that they have to cross, and they understand if they can cross the road or not. This is just what we are trying to rationalize with mathematics. So the curiosity to be that we have when we are kids, to ask always why this happened, why this cannot be lost. And then we have only to understand that we have tools, and these tools, the language of science is mathematics. These tools are the mathematical laws. So of course there is some effort to learn rules of mathematics, but if you like, if you have passion, if you are driven by passion, you can really overcome all the difficulties. Enough. You don't care. It's as when you like to dance, you can dance for hours. You don't care if you are tired or whatever. You just dance or whatever they like to do. So it's really passion and curiosity that they shouldn't forget about this, as if they were kids. In fact, we are all kids. We just
So
play.
I don't want to interrupt, but there's one more question if we have
Yeah.
time. Let me just check for
Yeah,
Sonia.
ready in the
very
room
very
as well.
briefly, we are close to 11, and I know some folks might have to go back to their internships. So just really brief if we can.
Of course. So do you have questions in the room? I didn't really understand.
Sorry.
Oh yeah, there was one
Yeah.
question that will make really brief, and
We'll
then
try
this
to-
will be the last question.
Try to answer it quickly. So,
Just a sentence.
yeah.
Hello. Why does the detector produce that strong of a magnetic field?
Right, that's an excellent question. The very short answer is we need this very strong magnetic field because charged particles will bend under a magnetic field.
Show this.
Will you share the screen real quick?
So if you don't have the magnetic field, you can't make a certain measurement about the particle's momentum. A high momentum particle will curve less. A low momentum particle will curve more. And so if you didn't have the magnetic field, they would just be straight lines coming out of the center. But since we have the magnetic field, it looks more like in this picture.
Yeah.
And
So
also you can understand if a particle is positively charged and negatively. And from the point of view, for example, matter antimatter, this makes you able for a charged particle to understand if you have, for example, in the picture that you see, a muon or an antimuon, because the muon is negative, the antimuon is just a positive muon. So you can really distinguish between particle and antiparticles for charged particles. And this is why you need a magnetic field.
and yeah, so that's the short answer.
Yeah.
We want to have as strong a magnetic field as possible because then even the very, very high momentum particles get bent and in order for us to identify their momentum. And that's one of the key things. We need to know the momentum of these particles to investigate how they behave. Okay, we have one more question in the Q&A, but maybe let's get if there's anyone else in the room.
Sure, but we will have a hard out for 11 for our time.
All right, we'll try to be very quick.
So if the photons and electrons can be detected inside the calorimeter, how do you detect like the momentum of the muons that travel through the calorimeter?
Okay, so we can maybe share again actually. So muons actually deposit, so they are charged particles, so you will see signals in the inner detector.
Can I say it like this?
Oh yeah, yeah.
If it reaches the outside edge, it's a muon.
Yeah.
There's hardly any detected
Yeah.
particle that, or any other type of particle that will make it to the edge that's a muon. And so in this picture, when you look, it does identify each particle. It shows they all stop at a certain layer. And so your question was about the energy deposited in the ecal. It's kind of the opposite. It's the fact that that particle deposits energy all the way out in the muon system. That's what tells us it's a muon. If a particle stops at the ecal, it's much more likely that's just an electron or a photon.
Yeah, this is what happens in the atmosphere. Basically, all the cosmic rays that are going through the atmosphere, all the particles that you form through the, let's say, the interaction, these are called the particle showers, everything is absorbed but muons. And this is why we have muons at the sea level. We call them the cosmic rays at the sea level. Now, if you see this picture from the top of the atmosphere to the ground, and on the ground you get only muons, is exactly what you see in the picture on the screen. So you have the collision points, and the particle who goes through is just the muon. This is why we put the muon detectors always at the edge of our detectors,
Okay.
because they are the only ones.
Sorry, so last 20
Yeah.
seconds, last 3 seconds, but if we have just a bit more time, there was a question in the Q&A about for the detector upgrades and just in general, how do we procure materials and technology? So at CERN, like how much are things developed, I guess, in-house, or are they developed at national labs like Fermilab, BNL? And the answer to this question is absolutely. So there's a lot of stuff that happens and is developed at CERN, but of course, Fermilab specifically contributes not just to the CMS detector. Fermilab, in fact, contributes. It's part of the CMS collaboration, so they don't work with the Atlas collaboration, but they have, for example, developed the quadruples that focus the beams just outside in the LHC. So there's immense collaboration and a lot of expertise coming from Fermilab and the national labs in the US, but likewise in other national labs around the world. So this becomes a really international collaboration, and there's a lot of stuff that goes into it, but that's as fast as I can answer it.
Well, thank you so much for your time. Let's give a round of applause for our colleagues over at CERN.
10 seconds over.
Thank you so much
Thank you to
for the
you.
virtual tour. We will be handed off to our next speaker over here, so that's why we had a hard out at 11. So enjoy dinner. Yes, and fellow alum of Kansas Rock Chalk. That's what I'll say.
Oh, Rock
and
Chalk.
all that. So, yeah. So yeah, and then our next summer lecture series will be on Thursday. We're still trying to finalize a room because we do have our Secretary of Energy coming. So we do have Don Lincoln, if you are familiar with him. He is our YouTube extraordinaire for Fermilab. So he will be doing his talk on the theory of everything. So again, thank you and have a great day, and have a good evening over at CERN. Thank you so much.
Thank you.
Thank you. Have a nice evening. Ciao, ciao.